Welcome back, everyone, to the fundamentals of mechanical design. Today we're actually going to step it up and we're going to move beyond the basics. We talked materials, loads and stresses, deflections, stiffnesses, strengths, all of that. Now we're ready to take it to the next level and to discuss exactly how it is that things are failing and what the proper way is to think about it from a mechanics perspective. You ready? Let's get to it. Okay, so when we talk about fracture, we're talking about statically loaded parts failing, okay? These are things that break in two or more pieces. They become permanently distorted. There's a couple other ways we can think about this, but most useful is to think about just hitting something and then it breaks, or to think about torquing something too much and then it breaks, or to think about something has too much pressure and then it breaks. We also need to remember the type of material that we're concerned with. Remember, ductile materials, they'll stretch before they break. They'll go further than 5% stretch before they completely fracture. Brittle materials will not. That's how we make this distinction. The Shigley's book has a great diagram, a flow chart for kind of diagnosing when to use any given theory of when things will fail. And today we're going to talk about the simplest theory, both on the brittle side as well as on the ductile side. So what you need to really keep in mind is that all of these are based on previous discussions we've had, principal stresses and maximum shear stresses. It's pretty straightforward. We've got a maximum normal stress theory and a maximum shear stress theory. After we kind of do our thing and do our analysis of forces and stresses in 3D, this is sort of the general case, we have all of these different stresses that we can use. However, to keep it simple, a lot of times we just use a plane stress analysis. And remember, that plane stress analysis is sort of telling us that the maximum shear stress is about half of the nominal normal stress on a simple 1D bar in tension or compression. And we can sort of say, okay, the flip side of the stress is the required strength. That's my S versus my sigma. So what this is getting at is it's saying that the maximum shear stress theory is just going to be the difference between the maximum normal and the minimum normal stress divided by 2. Okay, so about 50% of that nominal normal stress at yield, okay? Similarly, and even more simply, the max normal stress theory is just saying that failure occurs when you have the stress that's above or equal to yield. So what we're really saying is that the yield strength in shear is about half of the yield strength in tension. And that's kind of the bottom line. But that's also very conservative because we're considering a plane stress thing. We're not considering 3D, and we're keeping it very simple. So these simple models are great because they're intuitive, but they don't necessarily apply to materials that might have different strengths in tension and compression. And they also don't necessarily apply to stress and strain conditions that require a three-dimensional analysis. So if we need to do things with special materials or really complicated loading conditions, that's where we're going to fall into those most oft used modeling categories. So let me just show one example for today. Instead of using this simple max shear stress theory, we can use something called a von Mises stress, and you can do it either in principal stress form, or alternatively, you can calculate this based on all of your three-dimensional stresses, and you can probably guess that we don't do this very much by hand, but computers, they do this all the time, and that's what we want to take away from today.